Hi everyone, let's start section 2 of chapter 3, and this is part 1 video. So in this section 2 of chapter 3, we will have the design approach of discrete event simulation. So we will see how we can formulate a system, a discrete event system in terms of discrete event simulations, okay? It will be done through two steps, static modeling and dynamic modeling. And we'll have two examples in this section. In order to formulate a system in terms of discrete event simulations, at first we need to define its components. So this will be the static description of the system, and then we need to describe the dynamic behavior of the system and the interactions between the components, and this step is called description of dynamic relationships. So by doing these two steps, actually we are formulating the system in terms of discrete event simulation model. Okay. So for formulating a system in terms of a discrete event simulation, at first we need to define its components. They are entities and then attributes related to entities. And then system state, how we are going to define this system state at any time. And then events that we have in the system. And then activities and delays. So by defining these 5 items, or 5 components, actually we are describing the system in terms of static descriptions. Then we need to go for the dynamic behavior of the system. And so for system state, we need to obtain the initial state of the system at time 0. Then what event should be generated at time 0 to start simulation? So yeah, what's the initial status and how simulation will be started? What event will trigger starting of the simulation, and what kind of state variables we need to define for the system in order to describe the dynamic system's state. Okay. Then for events, so we have events, and events are going to be occur in the system. So we need to define what's the impact if any of these events occur. So the impact of occurring the events on system state, entities, attributes, and also the sets that we have or list. So we will actually formulate here the impact of occurring events on these items. And for activities, we need to define how we are going to obtain the time durations. It could be deterministic or constant, or it could be probabilistic. We can have a distribution for that time duration, or we can actually formulate this by a mathematical equation. Okay, and for activity, actually, what event makes the begin or end of the activity? So what event will trigger beginning of an activity, and what event will end it up actually? And can activity begin regardless of the system state, or certain conditions in system state required to begin the activity? So here the conditions and situations that we need to have in system in order to start an activity should be defined. And for delays, the events actually trigger the beginning or ending of the delay should be defined here, and conditions to begin or end of the delay. So by defining these dynamic behavior of the system and also static description, actually we are done. We are done on formulation of the system in terms of discrete event simulation. And the next step actually here is implementation. So we will implement these formulations in, let's say, a code, a Python code, for example. We can program the system by a program language, for example, Python, or we can implement these formulations in Arena. Okay, so after this step will be implementation, but this step is defined as design step actually. So by having these two descriptions here, actually we design a simulation model. Okay, let's have an example here. Here we are going to formulate static description during the first step for the bank teller system, which is a single server queuing model. So for this system state, we define two state variables, LQT and LST. LQT will be the number of customers waiting in line at time t, and LST will be the server's status. It could be 0 or 1, idle, or being busy serving customers. Okay. And for entities here, we have two types of entities, customers and tellers. So customers are the ones arrive the system to get service, and tellers are the ones who serve the customers. Okay. For attributes here, actually, we are not interested to differentiate customers or tellers. So because of that, we don't need to define attributes here. And events here, we have three types of entities: arrival of new customer, departure of customer, and end of simulation. So we need to actually define here that how we are going to represent event notice. So here we have this array, and the first element will be for the type of event. So A means arrival, D means departure, E means end of simulation. And the second element will be the occurrence time of the event. So for example, here we have an arrival, which will be happen at minute time, at minute 5, okay? And for the future event list, we just need to order the events in event times, right? So yeah, here's the first one would be arrival at time 5. The next one would be departure at time 6, and also end of simulation at time 30. Okay. For the activities here, we have two activities: inter-arrival time, which here we mentioned that it's exponential distribution with mean 5 minutes. Okay, and service time, or here we showed this that this is based on normal distribution with mean 4 and variance of 3, or standard deviation of 3 minutes. Okay, and the delays are customer wait time, and also we have another one as clock for this simulation clock, which will show the time t. Okay. So that was actually the static description of the system, and now we're going to have the dynamic description. So for the event, as you remember, we mentioned that for any event, we need to formulate its impact on the system. So here is for arrival event, and this special is for departure event. Okay, so here we are actually formulating the impact of arrival event on the system. So if we have an arrival event at time t, then we need to check if the server is available or not. If the server is busy serving other customer, I mean, if LST equals 1, so here this new arrival will join the line, so we'll increase the number of customers waiting in line by 1. But if the server is available, this means there is no line. So then the server becomes busy serving this new customer. And here, since we just started an activity, right? Starting service means an activity. So we need to obtain its service time, right? So yeah, by having the definition for service time, we generate a service time for this service, and let's say it's S star, and then T plus S star will be the departure event of this customer. So I mean, the end of service will be at time T plus S star. So here we need to include this event, I mean departure event, in a future event list, and its occurrence time will be T plus S star. So since it's arrival event, at any arrival we need to generate the next arrival event. Okay, so here we generate inter-arrival time A star for the next arrival, and then the arrival time for the next arrival will be at time t plus a star. Okay, so we need to include these two new events, departure and arrival, in the future event list, and they will be positioned in the future event list based on their occurrence time. Okay, and then we need to collect statistics and then return control to time advanced routine to continue simulation. That's for arrival. For departure, if at time t we have a departure, again we check if there is any customer in line. If it's yes, then we reduce the number of customers in line by 1, and then serving that new customer, that customer will be started right away. So we need to, again, same as before, we need to generate service time for this service as a star, and again a new departure event will be scheduled for time t plus s star. Okay, and if there is no one in the line, then the service status turns to 0. This means that server will be idle from this time, from time t. And at the end, we collect the statistics and return control to time advanced routine to continue simulation. Okay, so this is actually how we formulate the impact of occurrence of the events on the system. Okay, here we have integrated those two flowcharts in one flowchart for the whole simulation model. And as you see here, after initialization, we take the min time, the imminent event in the future event list. And then if it's departure, we go to this branch, will be the flowchart for departure. And if it's not, we go to this branch, and it will be the flowchart of the arrival. Okay, and for the collect statistics, actually we usually collect this one type of event and time of the next event, queue length, and number of servers busy if it's multiple server, and number of customers in the system or line. Okay, for the performance measures of this system, we can calculate the time weighted average queue length. Actually, you did this on assignment 1 in Excel, so you know how to calculate this. So to do so, we need to obtain the area under LQT and divide it by the simulation end times. So as you see here, integral over the time of LQT divided by the TE. So if it divide the area under LQT by TE, then that will be time weighted average queue length. But if we divide that by C, the total number of customers departed from the system, then that will be the average waiting time in queue per customer. Okay, and the maximum queue length could be easily obtained by taking maximum on LQT. Okay, and for the server, we can easily obtain the total server uptime and server utilization rate by dividing total server uptime by TE, the total time of simulation, and also 1 minus the server utilization will be the server idle rate. Okay. For the simulation terminating conditions, let's see what are the alternatives. The first one could be a fixed number of customers enter the server, and or fixed number of customers completed service. For example, 100 customers departed from system after the service. So if you remember, we actually usually do simulation in Excel based on this criteria. So we usually actually run simulation in Excel for 100 customers, 1,000 customers, and so on. And or fixed total simulation time, like we had in example before. So it's simulation end time. And usually in discrete event simulation, we consider this criteria. Usually we actually run the simulation for a predetermined time length. So yeah, actually this is the one that mostly used in simulation for discrete event simulations. And or all customers arrived before a predetermined total simulation time. So yeah, so these ones are actually alternatives for simulation terminating conditions, but usually for the DES, we consider this one fixed total simulation time. Okay, so this was the first part. In the second part, we will have an example for multiple server model. Okay, thank you.